Welcome back. This is part 2 of my talk. So we talked about roughly what the two theorems are that we're going to see. We're going to basically characterize being calibrated as saying that calibrated means that it's critical with respect to variations of the ambient metric. The volume functional is critical with respect to variations of the ambient metric upstairs in a certain special class of metric variations that are somehow obtained by varying the calibration form. Okay, so let's look at this explicitly in the first case, which is the case of a structure. So I remind you, we have an even dimensional, a 2m dimensional Riemannian manifold with a Riemannian metric, an almost complex structure which need not be integrable, and the associated 1-1 form, which is called the Kähler form, but it need not be closed. Okay, these are also called almost Hermitian manifolds. So this is what I just said. J is a G-orthogonal almost complex structure, and we define omega by this formula. It turns out to be a 2 form, a 1-1 form, and we do not assume omega is closed, and we do not assume that J is integrable. Of course, if both of those hold, if these both hold, then that's called a Kähler manifold, right? But in general, we're not going to make either of these assumptions, so it's just a manifold with a structure. So what we're going to do is we're going to take the form omega and we're going to vary it in the direction of exact forms. Okay, so we're going to have a varying, a one-parameter family of 2 forms omega, which is omega t, which is omega plus d of some one-parameter family of 1 forms, alpha t, where at time 0 we can take this form to be the 0 form, so that omega at time 0 is just omega. And let's call alpha dot the time derivative of alpha t at time 0. Okay. Then we're going to define a family of Riemannian metrics upstairs using this family of 1 forms as follows. This family of 2 forms as follows. So we're going to take omega t of xjy and omega t of yjx, add them together and divide by 2. This is our Riemannian metric. So you can show, first of all, that this is symmetric. And for t small enough, because it's a small variation of a symmetric, positive definite symmetric form, this will be positive definite. So for sufficiently small t, this really is a family of Riemannian metrics upstairs. And it's easy to check that what we've just done is we've said, well, omega t is a family of 2 forms, right? Our almost complex structure is fixed. We're varying omega, but not j. So we can always talk about the type PQ decomposition with respect to j. And even though omega is type 1-1, omega t may not be type 1-1. So what this construction is really doing is saying project omega t to its 1-1 part using the fixed j that's not evolving. And then this is exactly the formula you would use to get the metric g from the 1-1 form, the positive 1-1 form. Okay, so this is a family of metrics upstairs obtained by evolving the 2 form in the direction of exact forms. So here's theorem A. Suppose we have a 2k dimensional oriented submanifold. Remember, this is fixed, a compact oriented embedding. That's fixed. And suppose that it's calibrated with respect to this calibration form, this Kähler calibration form. And suppose we have a family of metrics in this special class of variations that I just described. Then there are 3 cases to this theorem in this case. If the real dimension is 2, if k is 1, then in fact this volume functional is constant, is independent of t. So certainly its time derivative at time 0 will be 0 since it's a constant function. If k is bigger than 1, then we have 2 subcases, right? Here we were saying that omega t varies in the direction of exact forms. So that means that the time derivative of omega t is certainly exact. Okay? Well, it may not be that the kth power of omega t also has exact time derivative. Suppose it does. So if omega t to the power of k has an exact time derivative, then in fact we have a critical point. And in the third case, again, if k is 1, now we're going to assume, certainly we're assuming that omega t has an exact time derivative, because that's the blanket assumption here. But suppose that it's not true that the kth power of omega t has an exact time derivative. But we can still say that we have a critical point for our volume functional if and only if this condition holds. We take d of omega, we restrict it to the submanifold L, and then we apply the map lambda, which is the adjoint of wedge product of omega restricted to L. So this lambda is the adjoint of wedge with omega restricted to L. Okay, this is the typical notation used for this operator on a manifold with a UM structure. And we notice that the condition we need in this case for it to be a critical point actually depends on L. This condition here depends on the embedding of L into M, which we've fixed. Okay? But it's automatically satisfied if omega is closed. Right? Because if omega is closed, then before I even restrict to L and apply this operator which depends on L, I'm still going to have 0. So this is important because when we get to the spin 7 case in the fourth theorem, we're going to have something slightly similar. We're going to get a condition that depends on the submanifold, which is a little bit unsatisfying. And we're going to want to say, well, possibly there's going to be some condition we can put on the torsion which will make this condition that looks like it depends on the submanifold hold in all cases. Okay, so I'll keep you in suspense and not spoil the punchline. We'll see what happens when we get to the fourth theorem. So this is theorem A in the case of a UM structure. I want to emphasize that this is not completely new, right? In the case when k equals 1, this theorem A was proved by Arezzo and Son when the manifold is Kähler. We don't assume anything about the torsion of this UM structure, which is nabla J. It's Kähler if and only if nabla J is 0. It's not really a new proof. We just observed that their proof actually works. As long as you keep track of things, their proof actually works even when there's torsion. Okay. Let me just sketch the proof. Since we have an almost complex submanifold, that's what our hypothesis was that L was calibrated with respect to alpha, which is omega to the k over k factorial. Since it's calibrated, we can find a special adapted orthonormal frame for M. We can find a local orthonormal frame for M such that E1 j of E1, E2 j of E2 up to Ek j of Ek are tangent to L, and then Ek plus 1 j of Ek plus 1 up to Em j of Em are normal to L. And then you can compute using this local frame that the time derivative at time 0 of this volume functional for this path of metrics is some constant, which is not important, it's non-zero, times the integral over L of d alpha dot. Remember, alpha dot was the time derivative of alpha t at time 0, wedged omega to the k minus 1. So this formula immediately gives you cases A and B of our theorem A. If I go back, when k equals 1, the functional is constant, and you can see that right here. When k equals 1, this goes away, and by Stokes' theorem, we're integrating something exact, we get 0. I'm showing it at time 0, but you can actually do this at any time t when k is 1. And case B, again, this you can write as d of omega to the k up to some constant. Okay, so it's basically a computation where the different cases come out, and to get case C, you rearrange this formula using Stokes' theorem, and you write it this way. And from here, it's easy to obtain case C of our theorem. Okay, that's a sketch proof. Let's look at theorem B in the case of a UM structure. So remember, theorem B says if it's critical, then the submanifold had to be calibrated. That's exactly what we're saying. So suppose that the metric G at time 0 is critical for the volume functional with respect to this special class of metric variations we just talked about. then the submanifold in fact has to be an almost complex submanifold. Okay, and here there's no cases. It works for any k, and it's the same argument. It's the following. So here's a sketch proof. So we take the following smooth function on M. Okay, so f of p is going to be 1/2 the distance squared from p to L. Okay, this is a smooth function on M, real valued function, and clearly it's non-negative because it's the square of the distance. And so this is how we define it near L, right, in a tubular neighborhood. And then we can just cut it off with a cutoff function, smooth it out to 0. We don't care what this function does away from L. We just care what it does near L. Okay? And of course, because it's the distance squared, it's always non-negative and it's exactly 0 on L. So this function, f, achieves its global minimum on L. So on L, it has to have 0 gradient. And you can also calculate that its Hessian on L, on the submanifold L, is just equal to the metric on the normal bundle. Okay, so if I take two tangent vectors to points on L and plug them into the Hessian, then it's just the metric applied to their normal parts. Okay, this is just a calculation. And using this function, and this function is important because we're going to use it for theorem B in all the cases. Using this function, we're going to take a specific class of variations in that class here, a specific choice. We're going to do the following. We're going to take the, alpha t to be any one parameter family of one forms such that its time derivative at time 0 is j grad f. Okay, so this is also called the symplectic gradient. Symplectic gradient. We take gradient of f and we rotate it by j. And if we do this, then you can just calculate that using an orthonormal frame, you do a calculation and you compute that the time derivative at time 0 of the volume functional for this particular variation, this one particular variation, turns out to be exactly this. Okay, there's some non-zero constant in front, which is not important, and then the integrand here is non-negative. This is non-negative. And our assumption was that we were critical for all of these types of variations. So we're definitely going to be critical for this variation, and therefore this thing has to be 0 because it's non-negative and it integrates to 0. Well, if that's 0, each of these things is 0, and that means that for each tangent vector to L, if I apply j to it and then project to the normal part, I get 0. So what that means is that j of EA is tangent to L for all A, and therefore j takes tangent vectors to tangent vectors, so it's an almost complex submanifold. Okay? Again, this converse, this theorem B, was originally proved by Arezzo's son when the manifold is Kähler. But we didn't have to assume anything about the torsion. It's still true no matter what happens with the torsion. Okay? So that was theorem B in the UM case. We're going to move on to the G2 case next. So this is another good place to stop and continue in video number 3.